In this lesson, just rewrite the date today, please. So in your notebook, I advise you to open your notebook and write the date today. The date today is 13 to 2024. And this topic in the course book, page 111. So it is in page 111. Let us start with describing the waves in that way. Waves that move through a material or vacuum are called the progressive wave. So the progressive wave can be travel through the medium or vacuum. Progressive wave transfers energy from one position to another. This very important statement, progressive wave transfers energy from one position to another. Now we see that figure in front of you. It is displacement distance. Take care. So here, this is displacement. Can you see here? This is displacement on y-axis, distance. We have another graph, displacement time, but we talk about displacement distance. Now, in displacement distance, we have many important definitions you have to memorize, please. The first definition, displacement. The displacement denoted by x, it is the distance of a point on the wave from its undisturbed position or in equilibrium position. So here, so the distance of this point, for example, this is the point A. The displacement of the point A, it is the distance from the equilibrium, the zero position. You have to remember that definition because the definitions are important, will come in the exam, in the final exam. So displacement is definition. So you write in your notebook, please, this is a definition of displacement. It is the distance of a point on the wave from equilibrium position. Amplitude, also, this is a definition of amplitude. It is the maximum displacement from equilibrium position. So the amplitude here, can you see here? This is the amplitude. It is the maximum displacement from the top. The top is called the crest. So the distance from crest to the center is called the amplitude, denoted by A. So the amplitude definition is that the maximum displacement from equilibrium position. Also, we have another definition, the wavelength. It is the distance from any point on the wave to the next exactly similar point. Or we can say it is the distance from crest to successive crest. So the distance between two crests is called the wavelength. We have to write the definitions in the notebook because they are important. Yes, question? Any question? Yeah. We studied that definitions in grade 11 before, but they are important also in grade 12. Now, definition of the time period. The time period denoted by T, it is the time taken to one complete oscillation, the time of one wave. The frequency definition also, the frequency is the number of oscillations per second, or the number of waves in 1 second. The relation between the frequency and time period is that the frequency measured in hertz, the frequency equals 1 over T. So this is the very important relation. Also, we can say the time period equals 1 over the frequency. Please write that definitions in your notebook, please. Later on, you can write this, but this is important. I will send this worksheet to you after the lesson, don't worry. But you have to write the definitions in your notebook, and you have to write the title describing the waves in your notebook, please, because I will not repeat this lesson again. Okay, guys? Any question, please? Any question? Okay, now, we go to this example. Try to solve this example, please. I give you a few seconds to solve. Determine the wavelength and amplitude of each of the following waves in front of you, we have two waves, wave A and wave B. Try to solve it alone. I give you a few seconds to solve. You understand the question? Okay, now I solve with you. For wave A, now look at wave A. Wave A is the blue one. In wave A, we need what? The wavelength. The wavelength, it is the distance between two successive crests. So this is a crest, and this is a crest also. The distance between the two crests on the wave A is called the wavelength. It is 15 what? Centimeter. Then lambda, the wavelength of A, denoted by lambda. So lambda for the wave A is 15 centimeter. And the amplitude denoted by A capital, it is the maximum displacement from the center. This maximum is 4 in centimeter. So the amplitude is 4 centimeter. So this is the answer for wave A. Now, what about the wave B? The wave B is the red one. Can you see? One wave, one complete wave takes 20 centimeter. So the length of one wave is 20, the length of the red wave is 20 centimeter. So lambda of wave B is 20 centimeter. What is the amplitude of wave B, the red one? The amplitude is the maximum displacement, which is 2. 2 what? 2 centimeter. So this is the answer of this part. Any question, guys? Okay. Any question? Just a minute, I bring my calculator, please. Okay, are you ready to the next? Next part is very important. Yes, question, Mister. Why land in wave B is not 25 centimeter? Very good. In wave B, it is not 25. Look, my friend. If you take the distance from crest to crest of wave B, this is the crest of wave B. Can you see? The maximum. And this is the crest. So the distance from crest to crest is the wavelength. Now, it's from 25, it's from 5 to 25. So lambda equal 25 minus 5, it's 20. Look, it is the same answer. If you take the crest to crest. So we can say the wavelength, it is the length of one wave. This is one wave. Or if you have crest to crest, you can say this is the wavelength. So you can choose any 2 points, the same points on the wave. Or we say 2 points in phase of the point of the wave. I answer your question. Okay, ready? Now, next, please. Ready? We talk about the phase difference. This is very important part. Take care. Again, this very important part. The phase difference. Now, here we have displacement distance graph and the displacement time graph. Here, can you see? I draw here displacement, distance graph. So maybe we have one wave or two waves, but it is the same idea. For example, this is a one wave. What is the phase difference between 2 points on the wave? For example, this is point A and this is point B. We need the phase difference. Okay? Now, the phase difference between 2 points on the wave, if we have displacement distance graph, if the distance between the 2 points is d, and we know that the full wavelength is lambda, then the phase difference between the 2 points is 2 pi d over lambda. D is the distance between the 2 points, and lambda is the total wavelength. So if it is displacement distance time graph, the phase difference between the 2 points is 2 pi over d. Type. If it is displacement time graph, another graph here, displacement time graph. And here we have this graph. Can you see? This is displacement time graph. Let the time between 2 points on the graph, for example, this is the point A and this is the point B, and let the time between the 2 points on the graph denoted by t small. The time period is t capital. So the phase difference is 2 pi t small over t capital. So we can get the phase difference in 2 ways. It depends on the given. If the given is the displacement distance, we use 2 pi d over lambda. Keep this in your mind because it's very important. It is not in your book, but it is very good way to get the phase difference. The phase difference is very important in the final exam. So the phase difference in radian, 2 pi, if it is in degrees, just to convert the pi to 180 degrees. So we can say the phase difference in radian, 2 pi d over lambda. If we need it in degree, it is 360 d over lambda. Okay? Now, the phase difference, if it is distance displacement time graph, it is 2 pi t small over t capital. T small is the time taken between the 2 points on the. Let us resolve this question. Any question before to continue, please? Yeah. Now, look at this question. Points A and B, points A and B are vibrating. They have phase difference is 360 or 0. They are in phase. They are in phase. The same, can you see here? Because the distance between the 2 points is lambda. Can you see? It is completely lambda. It's okay? Then the phase difference is 2 pi lambda over lambda. So it's 2 pi. So the phase difference between A and B is 2 pi or 360. 360 in mathematics is equivalent to 0. 360 degrees in mathematics equivalent to 0 in math. So we can say the phase difference is 2 pi or 360 or 0. They are in phase. But what about C and D? The distance between C and D is quarter cycle. Can you see? It's a quarter cycle, okay? So what is the phase difference between C and D? Again, the phase difference denoted by 2 pi d over lambda. D here is quarter cycle, quarter lambda. It is quarter cycle. Half cycle from 0 to D. Then the phase difference between C and D is 2 pi quarter lambda over lambda. Cancel lambda with lambda, so 2 pi over 4, it's pi over 2, or it's 90 degrees. So the phase difference between C and D is pi over 2, which is quarter cycle, or quarter lambda or 90 degrees. Take care. You have to understand the phase difference because it's very, very important. Now, look at this example and try to solve it alone. Take your time and try to solve it alone to check, do you understand or not? Okay. Now, we read the question together. If the time period t, so this is the time period, t capital. So the given is that t equals 2 seconds. And the time t small between the two waves here is 0.25 seconds. Calculate the phase difference between the two waves. Now, which formula? This is time. So the phase difference, okay, the phase difference equals 2 by t small over the time period t capital. Then it is 2 by multiply 0.25 divided by 2. By using the calculator, I said the calculate phase difference in degrees, So we replace 2 by 360, multiply 0.25 over 2. The answer is 45 degrees. So this is the phase difference between the two waves. Look at that 3 important examples. The two waves are in phase if they are starting together and ending together. This is very important for superposition. So this is wave A and the down is wave B. They starting together and ending together. So the phase difference is 0. They are in phase. Okay, so the phase difference, it is the distance between the two waves when they are starting. Now, for the second one, this is the phase difference. Can you see here? This is the phase difference. So the phase difference is 90. The blue one starts at 0. The red one starts at 90 degrees. So the red one is 90 degrees ahead of blue one. So the phase difference is 90 degrees or pi over 2. The third one, the blue one starts at 0. The red one starts at 180. Starts, it means the sine graph, like this. So the phase difference here is 180 degrees. When the phase difference is 180 degrees, we say they are anti-phase. So we have two important words, in phase or anti-phase. In anti-phase, it's 180 degrees or pi. In phase, so it is 0 degree or 360. Ready? Now, try to solve this question, please. Try by yourself. Yeah. Try to do this, please. Okay? Yeah. Two waves of the same frequency have time period. So this is T capital. So T capital here is 3 seconds. The two waves are out of phase by time difference 0.5 seconds. So this is T small, 0.5 seconds. Calculate the phase difference. When we talk about the time, we use the formula. He said in degrees. Can you see? In degrees. Then the phase difference equals 2 by T small over T capital. Or we can say 360 because we need the time, the phase difference in degrees, T small over T capital. Then the answer is 360 multiply 0.5 divided by 3. Okay, now we use the calculator. So 360 multiply 0.5 divided by 3. The answer is exactly 60 degrees. Now I give you another question. Try to write it and try to solve it. Okay? This question about the phase difference. Example for you. Two waves or 2 points on a wave, 2 points on a wave of wavelength of wave length 1.0 meter
مو ذا الشوي
are separated by a distance of 15 centimeter. Calculate the phase difference. Calculate the phase difference in radian. Try to solve that. Calculate the phase difference in radian. Now, think of the question. Here we have the distance. Here, the wavelength is 1 meter. And the distance between the 2 points, 15 centimeters. So we can convert centimeter to meter or meter to centimeter. Okay, we can convert meter to centimeter. Then the wavelength is 1.0 meter or 100 centimeter. And the distance between the 2 points denoted by D small, it's 15 centimeter. What do we need? We need the phase difference. Okay, yeah. Now, the phase difference equals 2 pi D small over lambda. We continue. So it's equals 2 pi multiply D small is 15 centimeter, wavelength is 100. When you use the calculator, it becomes 3 pi over 10. So this is the phase difference in radian. Any question, guys? Okay. Any question? By the way, I will not repeat this lesson. This lesson is official lesson. You have to write that in your notebook. I will send the file as PDF to you after the lesson. Now, next part of the lesson, we talk about wave speed. Ready? Look, please at this. For one complete wave, for one complete wave, this is one complete wave, okay? One wave. What is the distance traveled by the point on the wave? The distance traveled is lambda. For one complete wave, the distance or the length of one wave is lambda. What is the time taken for one point to start and end at the wave? The time is the time period. What is the speed now of that point on the wave? So the speed, we know that, is the distance over the time. So the speed of the wave, the distance is the wavelength, and the time is the time period. But we studied before at the beginning of the lesson is 1 over t is the frequency. Then we can write the speed v equals the lambda multiply the frequency. So this is the formula of the speed. So the speed denoted by v equals the lambda f. By the way, we take two important notes about the relation between the speed and the lambda. So this is very important. Note, I will write this. Note that in the same medium, the speed is constant. The speed of wave is constant. In the same medium, For example, in gas, liquid, or solid, the speed of wave is constant. In the same medium, the speed V of wave is constant. So what is the relation between lambda and the frequency? It is inverse relation. So when the frequency increases, lambda decreases and vice versa. This is in the same medium. What happens if the wave transfer from two different mediums? For example, from air to glass, or from air to oil, or from oil to water, or from water to oil. Different mediums, it means the different densities, so it will be different speeds. So the speed is not constant. What will be the constant? The frequency. So remember that in different mediums, okay, the frequency will be constant, is constant, because it depends on the source of the speed. Then what is the relation between lambda and the speed? It's a direct. Lambda proportional directly to the speed. Then remember, lambda proportional inversely to the frequency in the same medium. Lambda proportional directly to the speed in different mediums. So take care. It's like the relation between the electricity, if you remember the energy, the energies. Okay, now, so this is lambda and frequency in the same medium. So this happens in the same medium. This what? Sorry, in different mediums. Okay, so in different mediums, lambda proportional directly to the speed. In the same medium, lambda proportional inversely to the frequency. Now, let us solve. Take care. This note is very important for us because we talk about the waves. Now, ready? Please, now we solve this example together. Read the example, and then we start to solve together. Okay, guys? Here. Station radio has frequency kilohertz. So we have to convert it to hertz. It's 198 kilohertz. So it means 10 to the power 3 hertz. From kilohertz to hertz, multiply by 10 power 3. What if the wavelength? We need lambda. Carries by this. Okay, here we have the speed. So the speed, by the way, all electromagnetic waves travel with the speed of light. V equals 3 times 10 power 8. It is the speed of light in vacuum or air. Now we need lambda. Remember the rule or the triangle. V equals lambda multiply F. We need what? We need lambda. Then lambda equals V divided by F. V is the speed in meter, 3 times 10 power 8, divided by the frequency in hertz, 198 multiply 10 power 3. The answer will be 1515.2. The unit is meter. Okay, guys? Any problem, please? Okay. You have any doubt, please? Okay, yeah. Now, let us solve it. Try by yourself. Try to solve it. Okay, now. Sound is mechanical wave that can transmit it through a solid. Calculate the frequency, so we need F. Of wavelengths, we have lambda. Lambda equals 0.25 meter that travels through a steel at a speed. So this is the speed of sound in solid. It will be greater than the speed of sound in liquid, and in liquid greater than the speed of sound in air. The speed of sound in air is 340 meters per second. It will be less. So the speed of sound in that solid, it is 5060 meter per second. We need the frequency. Remember the formula, V lambda F. What do we need? We need the frequency. So the frequency equals V divided by lambda. Okay, now V equals 5060 divided by lambda 0.25. The answer is 202 by using the calculator. 40, the unit of frequency is hertz. Okay, guys, do you understand? Okay, now we talk about very, very, very important topic, the energy of the wave. Okay, so this important topic, take care, try to understand this topic with me. Wave energy, the energy of carried by the progressive wave. So the progressive wave, okay, transfer energy. So the energy is transferred by progressive wave. So the progressive wave transfers energy. Now we talk about what? Intensity. Intensity denoted by I. It is the amount of energy. Energy. Do you remember the energy? Passing through the unit area per unit time. The energy per unit time is the power. So it is the power per unit area. So the intensity, this is a definition of intensity. Intensity of the wave is the power per unit area. The intensity denoted by I, it is the power denoted by B over the area. The power measured in watt and the area measured in meter squared, the unit of intensity is what? Watt per meter squared. This is very important. So the intensity of the wave is the power per unit area. The power per unit area. The power measured in what? The area measured in meter squared. Now, we know that the area is by r squared. The area is by r squared. If the power is constant, so the intensity proportional to the area, which is by r squared. Because pi is constant, then we can say the intensity proportional inversely to r squared. So this relation, if the power is constant. Now, for a wave of amplitude A, this is very important relation between the intensity and the amplitude. So the intensity proportional to the amplitude squared. A is not area, A is the amplitude. Take care. So this A is amplitude. So more amplitude, more intensity. Also, we have a relation between amplitude and the energy. The energy also proportional directly to the amplitude squared. So the energy of the wave proportional to amplitude squared. We can say W or E both at the same. So how many relations we have here? Remember, the intensity, this is number one, equals the power per unit area. A is the area, take care. A is the area, okay? This is number one. And the intensity proportional inversely to the radius squared. The intensity proportional directly to amplitude. Take care. This A is amplitude. Okay? خلاص? Take care. This is amplitude. And the energy also proportional to amplitude squared. Amplitude. Take care. This is amplitude. It's okay? Take care. A, the first one is area, but the second two ones are the amplitude. Now let us we solve the questions to explain this. Okay, we can say the energy denoted by W, or we can say the energy denoted by E. Okay, amplitude squared. Now, look at example number 4 and try to solve it with me. Read the question. The amplitude of a wave in rope is 15 millimeter. So this is the amplitude. If the amplitude changes, then we have two amplitudes. So the first amplitude was 15 millimeter. If the amplitude changes to 20 millimeter, this is another amplitude, A2, 20 millimeter. Keeping the frequency the same, by what factor would the power carried by the rope? The power. Now, what is the relation between the power carried by the rope? Look, with what factor the power? The power and the energy, because it is the same time. So we can say here, the power, okay, proportional to the amplitude squared, okay? Or the energy carried by, because the rate of transfer of energy is the power. So we can say the energy proportional to amplitude squared. Then E1 over E2 equals A1 squared over A2 squared. A1 is 15 millimeter. Both are the same unit, so keep it 15 squared over 20 squared. When you simplify this, it becomes 9 over 15. Then the energy E2, when we do cross multiply, it is 15 E1 over 9. So the power increased by factor 15 over 9. So the power increased by factor 15 over 9. He said, what is the factor of the power? Any question, guys? Next question. Now we talk about exercises. Okay, let us we solve the question number 3 together. Look at number 3, please. He said, sinusoidal wave shown in the figure is traveling in the position X direction, has frequency. So we have here given the frequency F. So the frequency equals 18 hertz. He said, find from the figure the amplitude. This is the amplitude. It is half the total distance. The total distance is 8.26. The total distance, it means from crest to trough. This is crest and down is trough. But the amplitude is half the total distance. So in part A, the amplitude equals half the total distance equals half multiply 8.26. Yes? Yes? So the amplitude is 4.13 something. The wavelength, here we have the distance from crest to trough. It is half wave. Then the other half is 5.2. Then the wavelength, it is the distance between two successive crests. It's 5.2 times 2. So lambda is 5.2 multiply 2. So lambda equals 10.4 centimeter. The time period depends on the frequency. 1 over the frequency, it's 1 over 18 seconds. This is the time. We need the speed of wave. V equals lambda F. If lambda in centimeter, the velocity it will be in centimeters. So we can say 10.4 multiply the frequency 18. So the answer will be centimeter per second. So this is the wavelength. Okay, guys. Now we solve the question number 4. Look at number 4, please. Waves from source have amplitude 5 centimeter. So the amplitude is 5 centimeter carried and intensity. So when the amplitude is 5 centimeter, the intensity of the wave is 400 watt per meter squared. Look, the amplitude here, the intensity in watt per meter. It's okay. We can change the centimeter. No, it depends. It's watt per meter squared. What is the required? If the amplitude increased to 10, now this is a 10 centimeter. Because it's ratio, we don't need to convert the unit. We need I2. What is the relation now? The intensity, we said that the intensity is proportional directly to the amplitude square. Then I1 over I2 equals A1 squared over A2 squared. Now, I1 is 400, I2 is required. A1 related to I1 is 4 centimeter, but take care, it must be square. I do not change a centimeter because A2 it is in the same in centimeter. So it is 10 square. Do cross multiplication, you will get here the amplitude. But first I simplify this fraction. 4 squared over 10 squared. The answer is 4 over 25. 4 squared over 10 squared. Oh, not 4, it is 5. So it's 5 squared. Sorry, 5 squared. 5 squared over 10 squared. It's 1 over 4. When we do cross multiplication, so the intensity is 4 times 400. It is 1600. What is the unit now? Watt per meter squared. Okay, guys. The rest of the questions will be a homework for you. Try to solve. Yes.
In the question, the amplitude in centimeter, not in meter.
Yes, no problem, because it is centimeter up and centimeter down. If you convert it, you will cancel. No, you will get the same answer if you convert to meter. No problem.
Sure.
Welcome. Yeah. Now the rest of the questions will be a homework for you. It's okay, guys. Do the homework today to understand this lesson. This lesson is very important. I will not repeat the lesson again. Please register the lesson in your notebook. Okay, Shabab? Yalla. See you next time. Yalla. Salam alaikum.